So amines are so this is the functional group. They are the derivatives of ammonia, okay, NH3. So this ammonia, it has 3 hydrogens and 1 lone pair of electrons. So it is sp3 hybridized. Okay. So it's all, most of the reactions of this is due to the lone pair of electrons. Okay. Just 2 electrons. These are, so that makes this one basic. Okay. It makes this lone pair makes this one both Bronsted and Lewis base. And this just the example I'm giving you is ammonia. Here nitrogen is delta negative, hydrogen is delta positive. So this hydrogen is fairly acidic. Okay, acidic. So because of this carbon and nitrogen hydrogen bond, amine derivatives and ammonia, they have some acidic character as well. Okay, but not many reactions for this acidity. Mostly the reactions and properties is due to the basic character of amine. Okay, so this one you guys further see the basic. First I will talk briefly basicity pattern of this ammonia. So ammonia, when there is an alkyl group is present, carbon R, okay, then it will have 2 hydrogen. So this is considered as alkyl group is electron donating. Okay, it increases the electron density on nitrogen, but it is not 100% true. Just for the simple picture for you guys, and this R group donates electrons, so it increases the electron density and it will increase the basicity. So like this alkyl amines are more basic than ammonia. Okay. So if you will have one more, so that is called the secondary amine, it will be more even more basic. If you guys remember the handout for lab, okay, amine lab, read that one. It is Dr. Salahuddin has explained very nicely the basicity. You guys have already done the labs practical, but I will suggest you guys to read one more time. Okay, that will be very helpful to understand the basicity of amines. So this one will be more basic. Okay. As I said, this is not 100%. There are other factors as well. So we will not talk about in detail. So like tertiary amine, so 3 donating group, but the tertiary amine is less basic than secondary amine. It is also basicity is almost same as primary amine. Okay, some other factors here comes into picture. Okay, so the general pattern of these aliphatic amines. Now, if you see the aromatic amines, so aromatic amines could be 2 types. So here you see one is that nitrogen is outside the ring. Okay, the substitution for hydrogen. This is, they are called the anilines. Another in the heterocycles. Heterocycle reactions you guys can skip in this chapter, okay? But heterocycles basicity, general information you should know. So these are the aromatic amines. It could be 2 types, okay? Anilines and pyridine. So this is called pyridine. So this see the basicity of amines are due to the lone pair. So this lone pair here in anilines is in resonance with the ring. Let's say this one, you can write all the resonating structures. So don't forget to do practice, okay? In the book, there are so many resonating structures in this chapter. So do practice to write. So this is the resonating structure. You can write further like this here, and you can write other structures as well. So what do we see here? The lone pair is engaged in resonance with the ring. So it is not available that much. So the basicity of anilines are much less than the aliphatic amines. Okay, why? Because the lone pair is not freely available. It is in resonance with the ring. But in pyridines, okay, here pyridines are, see the lone pair is sitting outside the ring on nitrogen. Okay, it doesn't participate inside resonance. So here also the lone pair is free. So this because the lone pair is free, so pyridines are more basic than anilines, much more basic. But one thing remember, pyridines are less basic than aliphatic amines. Why? Because here the nitrogen is sp2 hybridized. See the nitrogen because of the double bond. So sp2 hybridized means higher s character. Higher s character means the electrons are closer to the nucleus, so that holds the lone pair more tightly. That makes this one less basic. Okay. S character increasing, S character increasing acidity. That is the reverse of basicity, remember. So here sp3 hybridization, so S character is 25%. Here sp2 hybridization, S character is 33.3%. So higher S character, lower the basicity. Okay. So these three different types of situation you guys remember. In anilines also remember, if there is an electron withdrawing group at ortho and para position, particularly, okay, like nitro, so it will pull the electron pair, okay, so that will make the resonance very effective even with the nitro outside, okay. So that further decreases the basicity of anilines. Okay. Electron withdrawing groups at ortho and para position. It will electron withdrawing groups will decrease the basicity at meta position as well, but they are more pronounced at ortho and para position. Similarly, electron donating groups will increase the basicity. Okay, here electron donating groups like OH. Okay, because this will increase the electron density here, so that will make this more basic. But the electron donating group cannot make it a stronger base than the pyridines or the aliphatic amines. Here, electron donating you can compare with aniline, and you compare with anilines, not the other ones. These will be like this one for hydroxyaniline will be less basic than pyridine and aliphatic amines. Okay, but here this one will be more basic than the simple amine or for nitroaniline. Okay. Clear. So read the basicity chapter, watch the videos I have discussed in detail. We have done some problems as well. Okay, any question? Okay, next, from the synthesis of anilines. So anilines are most of the reactions we have already discussed. Today we'll talk two, three new reactions. So what we have discussed, anilines can be synthesized Suppose if you have alkyl halide, CH3, let's say Pr, and you take potassium cyanide or sodium cyanide, what it will do? There will be SN2 reaction. Okay? Then the halogen will be replaced by cyanide. And this CN can be reduced to amine by lithium aluminum hydride reduction. This we have already discussed in the acid and nitrile chapter. So CH2 NH2. So this is one of the methods used to make this one. Okay. We can also make these amines from carboxylic acid in a two-step process. So carboxylic acid, see this one, if you have carboxylic acid, so first you convert this one to acyl chloride. Okay, by reacting with thionyl chloride, so it will make acyl chloride, which on reaction with amines, primary amines or ammonia or secondary amine, will be nucleophilic acyl substitution. Okay. Again, this one reaction with lithium aluminum hydride, amides are reduced to amines. Okay, so amides will be reduced to amines. So these reactions, you guys know, we have discussed before. Also, here you see, if you have alkyl halides and take ammonia, just ammonia, so what will happen? This SN2 reaction. So with SN2 reaction, it will make primary amine. But you guys know that primary amines are more basic, means that will be more nucleophilic than ammonia. So this reacts with another alkyl halide via SN2 reaction. So it makes a secondary amine. Okay. And secondary amines are more basic, more nucleophilic than the ammonia and primary amine. So it further reacts another SN2 reaction. So it will be RCH2 and CH2R, CH2R. See this, even this tertiary amine can react again. Another SN2 reaction. So this here it will make okay. This is the called quaternary ammonium salt. Okay, quaternary ammonium salt. So what happens if you try to react ammonia with alkyl halides? It will make all these 1, 2, 3, 4. Okay, in fact, it is a mixture of 4 compounds. So it says not a good method to make. Okay, so to make selectively a selectively primary amines, there is an alternate method. Okay, So for this, it need to take this reagent. This is called phthalimide. Remember here, okay, this one. Let's cyclic phthalic acid to phthalimide. If you take this one with a base NaOH, as I said, this one, the nitrogen hydrogen bond is polar. So due to this, it also shows some acidic character. So we'll take this one. What will happen here? Negative charge, sodium will be the counter ion, plus we'll have water. Okay. So this is a good nucleophile, this sodium phthalimide. Okay. So now if you take alkyl halides, so what will happen? SN2 reaction. It can react with SN2 reaction. So the nitrogen will be alkylated. So this is a new reaction we have never discussed before. So see the mechanism here. Okay? These are the stepwise things. So nitrogen will connect with the alkyl group. Okay. Then again, under basic condition, okay, like sodium hydroxide and water, what will happen now? This will react with the carbonyl. So nucleophilic addition to the carbonyl. Okay. So what will happen? It will make. So now next steps mechanism you guys have seen many times. It's a hydrolysis reaction. So it will be O minus OH. So here will be RCH2R. Okay. So this will come back and nitrogen will leave. The ring will open. Okay. So what will happen? So this. So hydrolysis of one of the carbonyl. Second step will be again hydrolysis under basic condition. Okay, this will go here, and what will happen? This will go here, and at the same time you can show that the nitrogen will take the proton from water. Okay, this here negative charge. This is the negative charge. We take proton from water. So what will be the product? R, and you'll have OH. Okay. So the final again the similar reaction from water. This will come back. It will open. It will happen here. Okay. So this is the primary amine. Okay, so primary, this is the kind of long mechanism, but here two reactions. Remember, SN2 reaction followed by hydrolysis. So this will make the product primary amine. So here you see this primary amine just is the pure, it is not contaminated by secondary or tertiary amine. So it's a very good method to make primary amines, and this is called Gabriel-Halimite reaction. Okay. Another reaction, two reactions we'll talk about for the synthesis of this primary amine. See, if you have an acyl chloride that I showed, okay, and react with ammonia, so it will make an amine, sorry, amide, which on reaction with a base sodium hydroxide and bromine, okay, will make amine with one carbon less. Okay, this one. Another similar reaction, if you take sodium azide, okay, sodium azide, remember this is the azide structure. The sodium azide. So it's a nucleophile. So it will do nucleophilic acyl substitution. Chlorine will leave. So RCO and triple bond. Okay. This reaction on heating with heat, the water followed by reaction with water will make the primary amine. Okay. So these are just two different similar reactions. So let's see the mechanism for the first reaction. See what happens here. We'll do this one first. So this is amide. It has acidic hydrogen. Nitrogen hydrogen bond is acidic. So under basic condition, it becomes a nucleophile. It reacts with bromine. See this one. It will take this proton and this will react. Okay. So what will be the product? The product will be RCO nitrogen BRH. Okay. Again, the base will take this proton. So it will make nitrogen minus Br. Okay. So here you see, try to understand this one. Here there is a rearrangement reaction happens. So bromine will leave. Okay. So what will happen? RCO nitrogen with two lone pairs. So how many electrons nitrogen has? 6 electrons, 2 lone pairs and 2 with the bond. Okay. So this is called nitrene. Remember, nitrene. There's an organic one, if you guys remember that carbocation, carboanion, carbene, carbon free radical. So similarly, carbene and here nitrene. So when this forms, so there is a rearrangement reaction happens. This R group will move on nitrogen, and this bond will come here to make a double bond. So what happened? R went to the nitrogen. So nitrogen has the R group. See, the nitrogen carbon double bond is forming, and the carbon has oxygen. Okay. So this functional group is called isocyanate. Okay. So this is very reactive. It reacts with water. So what will happen? It will go here, and this bond will take a proton from another water molecule. So what it will form? It will form ROH positive, CONHR. Okay. So here deprotonation. So deprotonation, what it will make? So deprotonation will make, I'm writing the same here, RCO, deprotonation will make like this in the next step. Okay. So then what will happen under heat is just, this is very, very unstable. Okay. So from another water molecule, it decomposes and it will take a proton from here. So it will make a primary amine plus carbon dioxide gas. So here is the driving force for this reaction, that the carbon dioxide gas formation it forms. Okay, so this reaction is called Hofmann-bromamide reaction. So this reaction to make an amine with one carbon less, that carbon is gone with carbon dioxide. So this is called Hofmann-bromamide reaction. Okay. So very quick, I will show you guys that another reaction, that acyl-azide reaction, that is the mechanism like this. Okay. So what happens, this one under heating condition, it will come here, this will go here. This is a resonance, you can write for acyl-azide. So we are writing resonating, another resonating structure. There is nothing in this. So here, negative charge, single bond. So azides are unstable. Okay. See, if you compare this one here with the previous slide, see, this portion was bromine in the previous slide. See this one here. See this is exactly, this is the structure here in the next. So what happened? This bond is very unstable, it breaks off. So what will happen? RCO nitrogen plus here nitrogen gas evolves. So what is this one? This is a nitrene intermediate. So where did we come? The same, this is the nitrene intermediate. From here, the same further reaction with water, it makes the primary amine and carbon dioxide. So the mechanism is same from here. Okay, so these are the new reactions. Okay,